Hello and welcome to Section 5.1 on the Fundamental Theorem of Calculus, Part 1, otherwise known as the Evaluation Theorem for Integration. In Section 5.1, we observe that the area under the curve of velocity is distance. That is, the integral of velocity is related to distance. This observation hints at a connection between integration and differentiation. The derivative of distance is velocity, and the integral of velocity is distance. In Section 5.5, we will explore this concept fully. However, in the meantime, let's jump the deeper theory and familiarize ourselves with the consequences, namely, the first part of the fundamental theorem of calculus. The definite integral of a continuous function f on the interval ab is evaluated by the difference of antiderivatives of f at a and b. Of central importance to the study of calculus, the fundamental theorem of calculus states that the integral of a continuous function f is related to an antiderivative of f. Letting the function g of x be the integral of f from a to x, the fundamental theorem says that g prime, the derivative of g, equals f. In other words, taking an antiderivative big F of little f, we can write big F as g of x plus a constant c. Now, big F of b minus big F of a can be written as g of b plus c minus g of a plus c. Canceling the c's and using the fact that g of a is 0, this follows because g of a represents a definite integral on a zero-length interval, integrating from a to a. We now have that big F of b minus big F of a equals g of b, which is the integral from a to b of f. This is the first part of the fundamental theorem of calculus, also known as the evaluation theorem for integration. The fundamental theorem allows us to sidestep limits in favor of antiderivatives. You may be surprised that an integral, which is defined by summing the areas of an ever-growing number of rectangles, can be computed with 2 points on a function. This result depends heavily upon the integrating function being continuous. Again, this result depends heavily upon the integrating function being continuous. Without continuity, you do not necessarily have the fundamental theorem, and you must integrate using limits. In most concrete examples, the velocity of an object is modeled as a continuous function. Therefore, the antiderivative of the velocity function is the distance function. The integral of the velocity from a to b is equal to the change of the distance on the interval a to b. Now that we have the fundamental theorem, antiderivatives become fundamental to integration. I recommend rewatching the video for section 5.3 on antiderivatives and studying the major antiderivative forms. For example, we can integrate the function x cubed plus sine of x with limits 0 to pi. Since x cubed and sine are both continuous, we can use the fundamental theorem by first calculating an antiderivative of the integrand. An antiderivative is x to the fourth over 4 minus cosine of x. The fundamental theorem states that the definite integral is the difference of an antiderivative on the interval 0 to pi. Therefore, the definite integral is pi to the fourth over 4 plus 2. Take another example. The function f of x equals 1 over x squared. This function has a single discontinuity at x equals 0, and an antiderivative of 1 over x. We can use the fundamental theorem to integrate f as long as 0 does not lie between the limits of integration. For example, we can see the integral between 1 and 2 is 1/2 using the fundamental theorem. However, we cannot calculate the integral between -1 and 1 using the fundamental theorem. In Calculus 2, techniques will be introduced to deal with functions and intervals for which the fundamental theorem fails to apply. In Section 5.5, we will study the fundamental theorem of calculus Part 2, the theorem which gave us the incredibly useful ability to evaluate the integral of continuous functions without resorting to limit calculations. You've seen the basics, now work towards mastery through practice and study.